Okay, today we're going to look at some problems from chapter 6, specifically section 6.1. We're going to start with exponential functions. We'll spend a few sections looking at those, and then we'll look at the logarithmic function. So remember, we defined an exponential function to be of the form y equals a times b raised to the x power. There's some restrictions on b, and that b has to be a positive number, and b is not equal to 1. So as long as we're in that form, then we have an exponential function. Notice the variable is in the exponent. For b, if b is between 0 and 1, so like 1/2 or 1/3, then we have what we call an exponential decay or depreciation, depending on the word problem. And notice that as x values get infinitely large, our y values keep getting closer and closer to 0, although they never reach 0. And if b is greater than 1, then we have what we would call an exponential growth or appreciation. So you could have the value of a painting, of an antique car, your money that appreciates when it's in the bank, gaining interest, as opposed to decay. We have some things in nature, radioactive materials that decay. Most cars, when they drive them off the lot and as you drive them, depreciate in value. They go down in value until they become a classic car, then they start to appreciate. All right, so we've got a few word problems that we're going to look at. That's going to be our focus here. And you're going to be using a graphing calculator for a lot of what we do, especially our word problems, very consistent with what we've done all year. And so here we have a graduate student studying bacteria as a growth rate. Okay, so let me just go back here for a second. So A in general is going to be our initial value. And then our problem will be 1 plus, we'll call it the rate of growth, raised to some time. And if it's depreciating, if it is going down in value, you have 1 minus the rate of growth, or decay rather, I'm sorry, or depreciation. So here we have a rate of growth of 15%. We start with 31,000. So the equation to represent the quantity of this at any moment in time, starting amount 1 plus the rate of increase raised to the time. 15% as a decimal is 0.15. And now we want to know how many in 20 days. So that's our t. So we have 31,000 times 1.15 raised to the 20th. So again, this is going to be used on our calculators. So we have 31,000 times, we don't really need the parentheses, but so I'm just going to write 1.15 raised to the 20th. And it does say to round our answer to the nearest whole number. So we would have 507,000. We're going to raise that, round that to the 3 there, so 363. Okay, next one, notice that we have this fox population. It is declining by 5%. So again, and we start with 9,700. So now we have 1 minus 0.05 raised to the t, because it's not going to be a negative, because remember our b cannot be negative. It has to be a positive number, and we want to know how many in 10 years. So we have 9,700 times 0.95 raised to the 10th. So that number here, right, that's how much we have left, 95%. If we're losing 5%, we'd have 95% left each year. So we have 9,700, whoops, one too many zeros, times 0.95 raised to the 10th. Again, it says round to the nearest whole number, so 5808. Okay. Let's see, our next one, half-life of a substance is 50 minutes. and you want to know how much is left after 150 minutes, and you start with 960. Okay, so what this means is that every 50 minutes, this goes down by 1/2. So that means our multiplier is going to be 1/2, but our exponent is going to be t divided by 50, right? Because if it was 50 minutes, that would mean it would go down by 1/2, so you'd have 1/2 to the first. So if it's 150 minutes, that's 3 of those. And notice when we substitute 150 in for t, right, 150 divided by 50 is 3, right? So we have 3 of our 50 minutes. So I changed that. That should be 960. Let me get that out of the light. Times 0.5 cubed. And that gives us 120 grams. Okay. We've got a few more here that we're going to look at. So here we have a colony of bacteria that's doubling every 3 hours. So it's very similar to our half-life, except we're going up by 2. So again, we would have how much we start with. Our base would be 2, but it's every 3 hours, so it's the t over 3. Right? Because if it's 12 hours from now, that's 3 of those, or rather 4 of those 3-hour time periods. And notice when we substitute 12 for t, 12 divided by 3 is 4. So again, over here we'll have 5,000 times 2 raised to the 4th, and that gives us 80,000 bacteria. Okay, we're going to look at a couple of interest rate problems where we're compounding it. So that gives us interest on top of our interest as opposed to just once a year. So very similar equation, right? Here's what we start with, 1 plus, but instead of 6%, it's going to be the 6% as a decimal divided by 4 because there are 4 quarters in a year, right? So every quarter we're getting 1/4 of that 6%. And then because we're going to compound it 4 times a year, we have 4t, right? Because in 1 year, you'd be wanting to compound it 4 times. And you'll see in 5 years, right, we would do it 20 times. So we have 4,000, 0.06 divided by 4 is 0.015. So 1.015, and then 4 times 5 is 20. So we have 4,000 times 1.015 raised to the 20th. And because we're dealing with money, we are going to want to go to the second decimal place for our cents. So that's how much money we would have after 5 years. And if you can find 6% annual interest in any bank account, you got to take it because that's not happening. Okay, one more interest rate problem. 9% annual interest, except we're going to compound it monthly. So that means it's 12 times a year. So we're going to have 12,000 times 1 plus 0.09 divided by 12 to the 12t. And then we're going to substitute 6 for t. So again, we have 0.09 divided by 12. That's 0.0075. 0075, and when we substitute 6 for t, 6 times 12 is 72. Okay, so again, we're going to have 12,000 times 1.0075 raised to the 72, because if we're doing it every month, that's 12 times a year, times 6 years, 72 times we've compounded our interest. And again, you'll never find this in the real world, but 20,550 and 63 cents. All right, hope that helps, and we'll see you soon.